This is Module 7 of Week 12. This is the final module of the course. In this module, we will continue and conclude our exam preparation and take up problems in kinematics, Newton's laws, and rotation. This is material we covered in weeks 1 through 4 of the course, or in study guides 9, 10, and 11. So let's start going backwards with rotational motion, and then we'll move on to translational motion. So here's a problem where an object is rotating such that its angular position, which is plotted on the y-axis, theta, varies as a function of time t, as shown in the graph. Find the angular acceleration of the object, okay? So this is a theta t graph, or the analog of a position time graph, and the slope of the graph is the change in the angle with respect to changes in time, and that's the angular velocity omega, okay? And so if I were to look at this graph and look at the slope, I would see that in this region of the graph, the slope is actually negative, okay, up till here, and so omega is negative in this part of the graph. And in this part of the graph here, the slope is positive, and so omega is actually positive in this part of the graph. So we're not actually after omega, because omega is the angular velocity. What we're actually after is the angular acceleration. So the angular acceleration is alpha, and so the angular acceleration is the change in the angular velocity with respect to changes in time, okay? And we can see from our argument here that you go from a negative angular velocity to a positive angular velocity. So the angular velocity is actually increasing with time, and so alpha is actually positive. And therefore the answer here is A, okay? So we're interested in angular acceleration in this problem. Okay. Another problem. Which statement best describes the Earth's rotation about its axis? Okay. Tangential velocity is the same at all points on the surface. Angular velocity is greatest. Angular acceleration is 0 at all points on the surface. Centripetal acceleration of a point on the Earth's surface is 0. Okay. So let's first draw a picture of what's going on in this situation. So there's the axis of rotation of the Earth, and the Earth is traveling around this axis of rotation with some angular velocity omega. Now the Earth rotates with a constant angular velocity, okay? It just does this. And so omega is actually a constant, okay? And so I'm going to just go through A, B, C, D almost sequentially and check off which are the statements that best describe this situation. So the first statement, A, is that the tangential velocity is the same at all points on the Earth's surface. Now, the tangential velocity is given by the perpendicular radius to the Earth's axis times the angular velocity, and the perpendicular distance to the Earth's axis is here, okay? But you can see that depending on what your latitude is, you can have a different perpendicular distance, okay? And so, right. So even though this is a constant, this will change. And so the tangential velocity will change depending on your latitude. And so this is not correct, okay? Part B, the angular velocity is greatest at the Earth's equator. Well, angular velocity is omega. And we've already said that the Earth rotates through a constant angle per unit time, okay? So the angular velocity is actually constant. And so B cannot be correct. Okay, C, the angular acceleration is 0 at all points on the Earth's surface. Well, the angular acceleration, again, is alpha, and alpha is d omega dt, and omega is constant. And so alpha is actually 0, and it is 0 everywhere. So this is actually correct. And then the final point is the centripetal acceleration of a point on the Earth's surface is 0 cannot be correct because any point on the Earth's surface, like here, is executing circular motion. And anytime you have a circular motion, you have a centripetal acceleration. And so that's actually not correct. So the answer to this problem is C. All right. So let's move on to a problem involving torque. So 3 forces are applied to a board that is held fixed in place by a nail, a black circle. A grid has been drawn on the board for your convenience, with each square having a side of 1 meter. If the forces with the magnitude shown, F1, F2, and F3, and this angle, what is the magnitude of the net torque about this point? Okay, and so what you need to do is calculate the net torque, and so you have to sum up the torque from force 1 plus the torque from force 2 plus the torque from force 3. Okay, and so let's just do this then on the next slide here. So again, I can calculate torque from 1. Okay, so the torque from 1, well, the first thing I want to do is actually define a direction and be consistent. So I'll define counterclockwise to be the positive direction. That's the usual convention. And then given that, I can look at force 1 and I realize that it's producing a torque in the counterclockwise direction, so it'll have a positive sign here, okay, about this pivot. And then the most convenient way to do this is to realize that I can calculate the torque if I just drop a line back here and look at this, okay? And so this is a perpendicular, and this distance here I'll call r perpendicular 1. And then I can use the formula that torque 1 is r perpendicular 1 times F1, okay, the magnitude of F1. And that is just positive. R perpendicular 1, there's 1, 2, 3, 4 boxes, so that's 4 meters times F1, which the problem said was 6 newtons. And so that works out to 24 newton meters just from torque 1, and it's positive. Okay, so then the other simple one to do is F3 or torque 3. Okay, now looking at F3 is going to create a clockwise torque, which is going to be negative, so I'll put the negative sign there. And then again, I can extend the line of force back and look at this. This is the R perpendicular 3, okay. So R perpendicular 3 is 1 meter. So I'll call it R perpendicular 3 times force 3. And that is negative 1 meter times the magnitude of force 3, which is 5 newtons. Okay. And then that gives me a negative 5 newton meter torque. And then finally, I come back to the slightly more difficult case of torque 2 because there's an angle involved with F2. Now, F2 is in the counterclockwise sense, so there's going to be a positive sign. And then I'm going to put in, instead, I'm going to use the formula with F2 perpendicular in it, and then just R2, where R2 is this distance here, R2. Okay, it's this distance here, which is 1, 2, 3, 4 units. And F2 perpendicular is just F, so this is plus F2 sine theta, okay, because F2 perpendicular is this or this, right, which is the opposite of the angle. So it's sine theta and R2. And so I can plug in the numbers there. I get plus F2 is 6 newtons, sine theta is sine 30 degrees, and R2 is, as I said, 4 meters. And so I get sine 30 degrees is a half, so I get 6 newtons, 1/2, 4 meters, which gives me a, sorry, F2 is 4 newtons. Sorry, so I get 8 Newton meters with a plus. And so then to calculate the net torque about the pivot, I add up plus 24 Newton meters, plus 8 Newton meters, and then minus 5 Newton meters to get 24 Newton meters to get 27 Newton meters, which, if you look back, is answer B. Okay. All right, the next question is quite interesting. Okay, so you have two buckets which spin around a horizontal axis on frictionless bearings. And what we're going to do is we're going to slowly fill the buckets with sand, pouring the sand vertically downwards into each bucket, okay, as it spins. And which of the following statements correctly describes what will happen and why, okay? And so what we're going to do is we're going to have some mass here, which is the sand, and some equal mass here, which is the sand, and that's going to be pouring down into these buckets, okay? And so at the end, you're going to add a mass m and m to these buckets. You're rotating around this axis with some angular frequency omega, which you'll have an initial and a final omega, and we'll call this distance here, just for the sake of notation, we'll call that r, the radius from the axis, and the axis here is, we'll call that the z-axis, okay? And so the question gives you various possible answers, and I think the thing to recognize about this problem is that angular momentum and angular momentum make an appearance in 3 of these questions. So angular momentum may be important, and energy appears in the other 2 equations. So energy conservation or lack of conservation may be important, okay? So the issue here, though, is that there are statements here about increasing and decreasing angular momentum. And what you have to keep in mind is that the angular momentum will change only if the angular momentum along this axis, the z-axis, will change only if there's a torque due to some sort of horizontal force in the plane of the rotating buckets, which causes some sort of angular acceleration of the whole system. Okay, the angular acceleration will change omega, and because L is equal to I omega, if omega goes up and I doesn't change, then the angular momentum will actually change, okay? And now, so you have to ask yourself, well, what are the forces in the problem and what are the potential horizontal forces? And the problem immediately tells you that the bearings are frictionless, and so the bearings inside this axis here are not actually going to cause any horizontal forces, which could lead to an angular deceleration, right? Slow the thing down. So we're going to ignore friction in the bearings. But given that, it's interesting to see whether there are any external torques in this problem that could actually change the angular momentum. And so we can draw this diagram here. There's, again, your mass m and your mass m, and it's acted on by some gravity force, mg, right? But the gravity force is actually pointing downwards, okay? So it's not a horizontal force, okay? So if this were to act and produce a torque, it would actually produce a torque about this axis, okay? But two things about this. One is there'd be a compensating torque which would prevent rotation like this about this axis coming from the bearings, okay? So the net torque would be 0. And the second thing also is that if you have equal amounts of sand here and here, this one will produce a negative torque, this one will produce a positive torque, which is exactly compensating. And so in fact, the extra gravitational force acting on the mass produces no external torque on the system, and certainly no external torque that's going to cause an angular acceleration around this vertical axis. And so to make a long story short, the conclusion that you can say is that the initial angular momentum is equal to the final angular momentum in this case, okay? So angular momentum in this problem is conserved, okay? Since there are no external torques. Okay, to change the L about this z-axis. Okay, so there's nothing in the horizontal plane that's speeding the system up or slowing it down. And so then with this observation, we can go back and start to look at some of the questions here that the thing raises. And so we can say, look at number C. The rotation rate increases because the sand adds mass to the system, increasing its angular momentum. Well, as I said, the angular momentum is conserved, so it doesn't increase. And the only thing that would increase the angular momentum is not adding mass to the system, but an external torque on the system due to forces in the horizontal direction. And so C is actually not correct. The rotation rate decreases because the sand decreases the angular momentum of the system. Again, a decrease of the angular momentum of the system would be due to an external torque, okay? And so this part D is not specific enough because it's not the sand that decreases the angular momentum, it's the external torque that decreases the angular momentum of the system. And so D is also not correct because we've determined that there are no external torques that would decrease the angular momentum about the z-axis in this system. And then B, if we go back to B actually concerns the total mechanical energy. It says the rotation rate remains constant because the total mechanical energy of the system is conserved. But that's actually not true, because if you think about it, when the sand comes down and hits the bucket, this is actually an inelastic collision, okay? There's a lot of dissipation in the sand. And so this is actually an inelastic collision, and so it's more than likely that the total mechanical energy of the system is not conserved. Okay, so this is not correct. Okay, and so we're left between choices A and E. Now, choice E is that the rotation rate increases because kinetic energy of the falling sand is transformed into rotational kinetic energy. Now, this is possible to transform translational kinetic energy into rotational kinetic energy, but the conclusion that would increase the rotation rate doesn't necessarily follow, okay? Because the thing you need to look at is the angular momentum conservation in this problem, okay? And so we need to apply angular momentum conservation, and then that will determine whether the rotation rate increases or whether, as in A, it decreases, okay? So let's do that now. So angular momentum is conserved, so Li is equal to Lf, and Li is the initial angular momentum, which is the moment of inertia initially of the, so this system has a certain moment of inertia, I, okay? And then I'll add in whatever potential initial angular momentum the sand has, and I'll come back to that later. And then the final angular momentum is just going to be given by the initial angular momentum of the buckets, plus then the extra moment of inertia, because you have two masses at a distance r away from the axis, which are rotating. So you have two masses at a distance r squared. That gives you an extra 2mr moment of inertia, and then you have some final angular velocity, because the whole system is rotating at some final angular velocity. And the question is whether omega f is larger or smaller than omega I. Now, let's look at the moment of inertia. Let's look at the angular momentum of the sand initially. Well, the sand is moving vertically downwards, so it's actually not rotating around this axis. And so the initial angular momentum of the sand, which would be its moment of inertia times its angular velocity, well, that's the moment of inertia times the angular velocity, which is 0, because the sand is actually just moving straight down. So it doesn't actually have any angular momentum around the z-axis in this problem. So the angular momentum of the sand is 0 about this rotation axis, z. And so I can ignore this, and then I can equate these two things. So I can write II omega I is equal to II omega I, II plus 2mr squared omega f. And what you can see is that this term in brackets is larger than II, and therefore, in order for this equality to hold, omega f has to be smaller than omega I. Okay? So the conclusion is that this system actually slows down. This is just like the situation where I was on this rotating thing and I got these two masses. And so the rotation rate doesn't increase, so E is wrong, but it does decrease, and it decreases because the angular momentum of the buckets and the sand system is conserved. Okay, so let's move on and do a few problems involving translational motion. Here's a problem where you have a block sliding, or a block on a plane, and the question is, under which of the following will the magnitude of the normal force be equal to mg plus f sine theta? Okay. So this is a little bit of a free body diagram problem. So I can draw in on these, the normal force acting on the mass and gravity acting on the mass, okay, plus the external force F, the normal force acting upwards, the mg acting downwards, and here mg acts downwards, but the normal force is normal to the surface, so it acts in this direction, okay? And so then we can balance, the first thing to realize is that perpendicular to the surface, right, there is no acceleration, okay? And we can use this fact of balancing the forces in the perpendicular direction to the surface to obtain the equation for the normal force, okay? Now, if I were to look at case 3, the expression that we're trying to get for the normal force involves F, and F here points up and down the surface. And so there's no component of F along the normal direction, along this direction here. And so what that means is that F will not enter into the force balance equation for N. Okay, N is going to be balanced with mg and some cosine of this angle. Okay, so this case 3 cannot contain F, And so case 3 and case 3 are eliminated. So this can't be right. The normal force will not have that form. So it's either going to be case 1 or case 2 or both. So if I look at case 1 and then I just balance, okay, I'll make this direction here positive, and I just balance mass times acceleration equals force along the vertical direction. Well, as I said, there's no acceleration along the vertical direction in case 1. And and this is net force. And the force is going to be given by N, and then mg downwards, and then this component of F, which is downward. So that's negative F and then sine theta. Okay, so if I solve this, I get N is equal to mg plus F sine theta. And so A, case 1 is definitely possible. Okay, so that eliminates B because case 1 is definitely one of the possibilities. But we now have to see whether case 2 also has this. But the only difference has this formula. But the only difference between case 1 and case 2 is the direction of the force. In case 1, it's pointing diagonally downwards. In case 2, it's pointing diagonally upwards. So that's just going to change the sign of the vertical component of force. And so for case 2, you're going to get mg minus F sine theta is equal to the normal force. And so that's not of this form because this form has a plus sign. And so it's only case 1 that has this form. And so the answer is A. Okay. Two more questions. So here you have two blocks of masses m and 2m, which are in contact on a level frictionless surface. A force Fp can be applied either to the large block, as in diagram 1, or to the small block, as in diagram 2. If the magnitude of Fp is the same in both cases, the force exerted on the small block by the larger one is the same, larger in diagram 1, larger in diagram 2, or depends on the magnitude of the force Fp. Okay. Well, this is identifying the type of problem this is. This is a free body diagram and an action-reaction force problem. And the action-reaction force is because of the phrasing, the force exerted by the small block on the larger one, the force exerted on the large block by the smaller one would be the reaction to that. Okay, so the way to approach this problem and is to realize, okay, first of all, it's a frictionless surface, so we don't need to calculate any forces in the vertical direction. They're not relevant because there's no friction, so there's no friction, which would depend on a vertical normal force. So we don't have to worry about that. Second thing we should do is probably just label a direction. So I'll make to the right is positive. And then the first thing I want to do is I want to examine the whole system, either diagram 1 or diagram 2, because the whole system, okay, well, in the whole system, let's say diagram 1, all right, then you have a net force, well, you have a total mass of 3m, okay, experiencing a net external force Fp. And so in diagram 1, you'd write Fp is equal to mass times acceleration, which is equal to 3m times a. So in diagram 1, then solving for a would be 1/3 Fp over m. Okay? And in diagram 2, you have the same thing. You have an external force Fp, now pointing in the opposite direction, in the negative direction, acting on 3m of mass. And so in this case, the acceleration is 1/3 Fp over m, but it's in the negative direction. So this is the acceleration in this way, and in diagram 1, the acceleration is this in this way. So that's important to note, okay? And then, so what I need to do now is to calculate the force on m, little m, the small block from the larger one. I have to draw free body diagrams of these two situations. Okay, so I'll just note this down. Keep in mind for the diagram number 1, you have an acceleration which is 1/3 Fp over m. And for diagram number 2, you have an overall acceleration which is negative 1/3 Fp over m. All right. And so let's draw the free body diagram for situation number 1. I have big mass 2m. It's acted on in situation number 1 by Fp. It has then a normal force acting on it coming from the small block, and the small block has only the normal force action-reaction pair acting on it. So this has mass m. Okay, both of these blocks, this is the thing that we want. Okay, this normal force N is the force exerted on the small block by the larger one, and it's equal and opposite to the N acting on 2m. Now both of these blocks are accelerating like this with an acceleration a given by this. And so for the smaller block, if we just balance the forces on it, we have F equals ma on the smaller block, okay? And the only force acting on it is N, and its mass is m, and its acceleration is a, which is 1/3 Fp over m. Okay? So in this diagram, then N is equal to 1/3 Fp. Okay, let's do a free body diagram now for diagram number 2. So I have a block with mass 2m. I have another block with mass m. The force now is acting on mass m from the right, and this there is also on mass m, there is a normal force acting to the right, okay, coming from the larger mass block, and the larger mass block here experiences an equal and opposite normal force in that direction, and the acceleration in this case is in this direction here, okay, and remember this is positive. So again, I want this normal force, okay, but I can obtain that normal force by calculating this normal force because it's an action-reaction pair, and so its magnitude is going to be given by the same quantity. And so I just have to look at this block, okay? So this block, if I just apply, so this is to the 2m mass, I apply F equals ma, okay? The only force here is negative n, okay, pointing in this direction. The mass of the block is 2m, and the acceleration of the whole system in diagram 2 is negative 1/3 Fp over m, okay? And so I get, in this situation, that negative n is equal to negative 2/3 of, and then canceling the m's, Fp, or n is equal to 2/3 Fp, okay? So 2/3 Fp is, again, n is the magnitude of this action-reaction, this normal force, but it's also the magnitude of the force exerted on the small block by the larger one, by Newton's third law. And so 2/3 Fp is larger than 1/3 Fp, independent of the magnitude of Fp, okay? And so then the magnitude of the normal force here is greater in diagram 2. So this is going to be greater. Okay. In diagram 2, and if I go back to the answer key, that is answer C. All right. Okay, so last question. You need to swim directly across a 200-meter wide river from north to south. So let's just draw north, south, west, east. Okay, there's your river. There's 200 meters across, and you're swimming directly across from north to south. However, due to a current flowing in the eastern direction with a speed of 3 meters per second, okay, so there's your 3 meters per second there, it ends up taking you 25 seconds to reach the far side. How quickly could you have swam if there was no current in the river? Okay, so if there's no current in the river, you can swim right across the river using your velocity relative to the water to cover the 200 meters of the river. And so this is a relative velocity problem. And I want to just label in, here's the ground, here's the water, and there is you, although you're actually swimming, okay? And then I can put in various vectors into this problem. Let me just do this here. Okay, I'll do this in blue. So you have this vector here, which is what somebody who's standing on the ground sees. So that's the velocity of u with respect to the ground. Then you have this red vector here, which is 3 meters per second. And that is the velocity of the water with respect to the ground. That's the current. And then you have the velocity that you actually have to swim at. That's the velocity of u with respect to still water, which is green. Okay, so if you swim out this way and then the current pulls you back, according to the ground, you would just swim directly across. Okay, and so this is relative velocity. And the relevant equation is that, according to this diagram, the velocity of u with respect to the water, which is the green curve, added head to tail with the velocity of the water with respect to the ground, which is the red arrow, is equal to the velocity of u with respect to the ground. Okay? And now the magnitude of the velocity of u with respect to the ground is what is observed, that you're traveling 200 meters across the stream and it's taking you 25 seconds. So that's a velocity of 8 meters per second. And so now you have a triangle here with one side is 3, one side is 8, and this side here is the square root of 3 squared, it's the hypotenuse, plus 8 squared. And so this is the velocity of u in the water. That magnitude is square root 3 squared plus 8 squared. That's the hypotenuse here. All right. And calculating that out, that gives you the square root of 73, which is 8.5 meters per second or 8.3 meters per second. I'm not sure what I wrote here. Anyway, that's the velocity. So that's the velocity that you can swim with respect to still water. So if there's no current in the river, you can swim across the river with this velocity, and the time it'll take you is the distance traveled divided by this velocity, and the distance is 200 meters, and your velocity is 8.5 meters per second, and that will work out to 23 seconds, okay, which is answer B in this case. Okay, so that's it for the taking up of these problems. I put up a PDF that has more practice problems on it than these with the answer key. And so you can use those to study for your exam, and good luck with your studying, and good luck with your exam in physics, and good luck with all your exams this term period. I know it's been a challenging term, but I think you've done really well and showed some true grit. And so good luck with everything, and take care. Bye-bye.